Thank you for the introduction, Jonas, and I wanted to thank TNG for having me come and talk to you guys about something that I happen to be very passionate about, and that's dynamic soaring, or DS, with radio-controlled gliders. Now, when most people think of radio-controlled gliders, they picture something like this. It's generally a very lightweight structure and quite fragile. It's intended to float around gently on thermal activity in the air, and it's a very relaxing pursuit. It's something you might do on a Sunday afternoon at the park, that kind of thing. But I'd like to play you guys a little audio clip. Max volume, please. So these sounds, it's kind of hard to make out on the audio system here, but they're not exactly the sounds you might expect based on the gliders we were just looking at. So let's take a look and see what's going on here. So what you're watching here is my latest design. It's the Transonic DP. It's 3.3 meters in span, and this is the second flight it ever had, where it set the hill record for Parker Mountain in California, and the speed was 448 miles per hour. I think that's roughly 720 kilometers per hour. So you can see that dynamic soaring is drastically changing the landscape of what it means to go soaring with an RC glider. So before we get into dynamic soaring, let's step back and look at the broader category of slope soaring. And slope soaring is possible anytime you have a hill with wind blowing against it. You can see the wind is deflected upwards by the hill, and it develops this vertical component of lift here. And as long as that vertical component of lift is greater than the sink rate of the glider you're flying, and you manage to keep it in this general area, of this general vicinity where the lift is produced by the hill, you can fly indefinitely. And this can go on for quite some time. People have been taking advantage of this phenomenon for a long time, since the advent of radio-controlled equipment back in the 50s and 60s. But the activity has always been confined to the front side, over here on the front side of the ridge. This area back here where it says danger has this reputation of being the part of the hill which destroys airplanes. Everyone who's been in slope soaring either has a story themselves or has seen a friend make the mistake of allowing their plane to drift too far back in the wind, and they get into this area behind the top of the ridge where the wind no longer has a vertical component to it. The result is the plane simply falls out of the air and gets caught down in this turbulence down here. And if they ever did find the plane after that, it was probably smashed into pieces on the backside of a hill. But that all changed when this guy came along. Joe Wirtz is a very well-known aerodynamicist, engineer, and very active in the RC gliding world. He's been the world champion in competition gliding for a number of different categories, a number of different years. A very prolific guy in the field. He was flying his foam glider. We make some gliders out of foam as trainers because when they crash, they don't break as easily. He was flying one at Parker Mountain in California one time. This was back in the 90s with a friend of his. And the friend's glider collided with Joe's glider. It lost control. And by the time he regained control of the plane, it was well downwind of the hill. The typical pilot would then point the glider into the wind and slowly watch a painful death happen as you just simply can't make it upwind. Joe, on the other hand, being who he is, had the wherewithal to choose to dive lower behind the hill, dive at the ground, straight at the ground. And he was able to get into the shadow, the lee behind the hill. And because he was out of the wind, he then made it back to the front of the hill. And when he did reach the front of the hill with his glider again, he realized the plane had way too much energy. It was coming way faster than it should have been. And that's when the light bulb came on inside Joe's head. And he realized this concept of dynamic soaring, which he'd read about and heard about for years, was actually a practical thing to pursue with RC glider. When you do DS, or dynamic soaring, when you do it on purpose, it looks something like this. Here you've got the wind coming up from the right side of the ridge. Here you've got that vertical component to it. And when it reaches the top of the ridge, it separates. And below, far below the hill, you have this area of relatively calm air. It's never completely calm, as you'll see later, but it's generally calm compared to the wind up above. And in between, where the moving air mass is making contact with the fixed air mass, you have this friction, and it causes these turbulent eddies to form, and we call that the shear layer. The typical models predict this shear layer to diverge from the ridge of the peak of the ridge at roughly 12 degrees. So this here, you have a time-lapse photo showing the practical, real-life version of what you just saw. Here you've got the guy standing on top of the ridge, and the wind is coming up from your right, and the backside is here on the left. And this circuit that he's doing looks a bit high, like his bottom turn might not be getting down below the shear layer, but that's because the slope on the front is very vertical. It's almost a cliff. So that's what it looks like when you do it right. So dynamic soaring, how does it work? You can spend a lot of time talking and trying to explain this concept to people that have never seen it or experienced it. But there's actually, I found the easiest way to explain it to people is someone has put an animation up on YouTube, and let's take a look at that. For this animation to work, we just have to exclude drag for the moment. That's a big exclusion, but we're going to come back to it in just a minute. So when you perform a 180-degree turn with a glider with no drag, you come out at the same speed you went in with. Now, if this turn is completed in an air mass which is moving, you can see your ground speed can change. It changes based on the velocity of the air mass which you're turning in. Oops. And so if we have two air masses, one fixed and one moving, and we cycle between the two, as we enter this headwind, our ground speed is not so great, but if we turn and we go downwind, we have the benefit of this tailwind with us. And every time we make this turn, the top turn we'll call it, we gain the ground speed equal to the amount of the wind speed that we're turning. We enter with a headwind and we leave with a tailwind, so that you can see the ground speed would increase. So now if we look at airspeed and ground speed throughout the circuit, we begin in a fixed air mass, and we have, obviously, ground speed and airspeed are matched. The air is not moving. We penetrate the shear layer into this moving air, and it looks like we've got a formatting issue, I'm sorry. The airspeed quickly jumps as we move into this headwind. The ground speed, if we remained at this orientation, the ground speed would eventually decrease. We've got this headwind to contend with, but we're going to do a 180 turn before we have this opportunity. And we make that 180 turn, the airspeed is preserved, and the ground speed is gained, like we saw in the previous part. And then when we enter the fixed air mass again, you have this sharp increase of airspeed, and that's because the glider is leaving a tailwind, it's entering a headwind. As far as it knows, it's entering this headwind of equal speed. And so the ground speed and airspeed are matched on the backside. When we come back to where we started, you notice we have much higher velocities in both cases. Now, without drag, if we kept on doing this every time we do the circuit, it doesn't matter how fast we enter the circuit, we always gain this airspeed jump. And so without drag, you could accelerate your infinitely fast glider. But if we bring drag into the equation, I'm going to use some stuff that Mark Drella, another well-known guy in the aviation or aerodynamics field and in the RC modeling field. He's a professor at MIT, and he quickly took an interest in this phenomenon of dynamic soaring with RC gliders. And so he built a simulator and an optimizer at MIT, and he produced these plots for us. And you can see this is based on my Kinetic 130-inch Kinetic DP in 45-mile-per-hour winds. And so the blue curve is the airspeed. Oops, that was the pointer. So if we start at the middle of the top turn, that's this far left edge on the graph here, our ground speed is increasing like we saw in the previous illustration. We're turning from a headwind to a tailwind, so our ground speed is going to be increasing. Our airspeed now, since we have drag in the picture, is decreasing. Our airspeed is going to decrease the entire time, except for when we have these shear crossings, when we have this quick jump in airspeeds. So the ground speed increases all the way to the point where we finish the top turn and we're entering the shear layer. That's when we have the full effect of the tailwind that's blowing up the hill. We cross this shear layer where the fixed air mass meets the moving air mass. And as we begin this bottom turn, our ground speed and airspeed are both going to decrease the entire duration of this turn. There's no energy to be harvested down there. It's a fixed air mass. And as you would expect, the ground speed and airspeed are closely matched. The air is not moving. So when we finish this bottom turn and we now are headed back up to the front side of the hill, we hit this shear crossing again. You get this abrupt jump in airspeed that represents the headwind that you're now entering. And then as you begin the top turn, there's this tilting of the lift vector that because the wind is now to the belly of the glider as you make this 180-degree turn, the lift vector is tilted forward. It actually generates thrust. And that's part of the conversion of this airspeed gain into ground speed gain as you turn in. You now have this full tailwind effect. So that was that's what it looks like in reality. This is after he ran it through the optimizer. The question was, well, we know what we're doing right now. What does the Optimum DS circuit look like for this type of situation, a shear layer behind a ridge? And it turns out it looks an awful lot like what reality has found to be optimum. It's a constant diameter circle. And a constant diameter circle translates to a constant lift coefficient. Now, lift coefficient is it's a gauge of how hard the wing is working to fly this circular path. And we can choose, we can adjust this for each glider and each wing loading to match this diameter so that the plane is always flying at its best L/D, or lift to drag ratio. That's going to be the most efficient configuration, and you'll get the highest speed for a given wind speed. We do find some things vary in real life. I believe it has to do with this wedge here, the turbulent shear layer between the fixed air mass and the moving air mass. I don't believe Dr. Drella's model might have taken into consideration some things which could be happening to the performance of the airfoil when it's in this very turbulent air here at high speeds. The theory is that the nice airflow that you get over the wing that leads to efficient flying might not fully pan out when you're in this level of turbulence. And so we find that stretching this circular orbit into an oval orbit actually yields higher speeds. We unload by flying a tight top turn and a tight bottom turn and two semi-straight legs in between as you go through the shear layer. Tends to unload the wing, and you're not asking as much of the wing under these conditions. So humans weren't the first to figure out this dynamic soaring thing. The black-footed albatross has been using this phenomenon for thousands of years to travel large expanses over the open ocean without ever flapping a wing. Lord Rayleigh was the first to note this and observe and note this phenomenon, and he termed it gust soaring, which, if you read his papers, it basically translates loosely to what we call dynamic soaring now. And you have even read that they can perform this maneuver in their sleep with their wingtip mere centimeters from moving water. So that's something we all aspire to, the skills of the albatross. Here graphically you can see what's happening. Like on the hill we have a slope and the wind blowing up the slope. When it leaves the top of, this is a swell in the water, by the way. When it leaves the top of the swell, it bridges across to the next swell, and there's this gap of lee eddy down below the shear layer. And the albatross is able to fly into the wind and into the still air, just like we do with a model airplane. But instead of these guys, they're usually trying to go somewhere. We're trying to go for speed. And so as a result, their path is not circular like ours. It's usually S-shaped, where they go into the lee and into the headwind and into the lee and into the headwind. And they can use this type of flying to go upwind, downwind, or any direction in between. And again, never have to put any energy into the system. It's all free. So dynamic soaring is that's one way of getting energy out of two different masses with two different velocities. There are much simpler ways. Sailing and windmills are very effective and very simple ways of extracting the same energy that exists when you have moving air mass. In the sailboat scenario, you have the keel, which is in the fixed water, and that way the boat is able to fully take advantage of the moving wind. And in the case of the windmill, you've got the mast holding the windmill fixed to the ground, and the blades are in the wind 100% of the time. This differs from dynamic soaring in that in both of these cases, you're able to remain in both mediums at the same time. You can harvest your energy all of the time. Whereas in a dynamic soaring vehicle, we have to cycle from one air mass to the other. We're effectively only harnessing energy half of the time, so we have to make it count and do it quickly. So in the early days of dynamic soaring, people quickly wanted to graduate from their foam gliders that were not so efficient to their competition gliders. F3X represents the F3B, F3J, different competitive gliding disciplines. And they're much more efficient airframes. They're made of carbon fiber, very precisely made. But they're so precisely made and so efficient that they were able to reach speeds at which the structure simply couldn't hold up any longer. The aerodynamic loads were just far too great for these models. And it led to a lot of spectacular video footage and mid-air failures and a bad reputation for dynamic soaring as being a destructive hobby. The two main failure modes we have, first and foremost, was the spar bending failure. As the wing is generating lift, as we're pulling really hard positive Gs to make this circular orbit, that's a lot of bending stress on the wing because the lift is generated outboard from the center line of the wing. And so the spar inside the wing would typically fail, a compression failure on the top spar, and the wing would fold in half. The other failure mode is flutter, and if you've ever rolled down your window and stuck a piece of paper or cardboard out the window and it starts shaking in the wind and then rips in half, you've probably experienced flutter. So here's a video of a spar failure.
The extreme power of the separation layer is demonstrated as Craig Tootleman's plane is eaten alive by Cape Blanco's infamous back door and smoking 40-mile-an-hour winds.
So strong winds tend to make a heavy object look very light. So don't be too far misled. That was a well-constructed model, just subjected to a lot of Gs and couldn't hold up to it. So flutter, the other failure mode, which was the main killer of DS models, it's a response of an elastic material when it's subjected to aerodynamic loads. It's often a coupling of torsional flexing along with bending of the wing. And one mode tends to exacerbate the other mode and vice versa. It's a runaway, unstable system. And the only way to stop it once it's begun is to decrease the speed of the vehicle. The onset of flutter is generally dependent upon the stiffness and mass of the component of the airframe which is fluttering, or the entire airframe in other cases, and the speed at which they're traveling through the air. And we have some examples of flutter here. Here they're flutter testing a full-scale glider. This has got a guy inside it, which is a bit scary. But it has to happen to any man-carrying aircraft before it can be put into service. And you see he obviously decreased the velocity and was able to keep it in one piece. Some pretty old footage, but you get the idea that flutter is a very destructive and often unpredictable failure mode, and hard to know exactly when it's going to happen. So when I got my feet wet with dynamic soaring with a foam airplane, and I saw these videos of guys flying these composite planes, and they're all blowing up in the air, and it struck me that dynamic soaring has all the ingredients I need to make it something that I could just dive right into and never look back. You can't imagine the excitement of getting in your truck and four-wheeling up a crazy steep dirt road that you don't think you can make it up, only to get up to the top and you're standing there with 100, 120 kilometer per hour winds, and you're struggling just to stand up in the wind. Rocks are blowing up from the hill, the face of the hill, and we have to wear ski goggles. It's a really exhilarating experience to be up there. And then you take your shiny new airplane that you've spent hours building, and you throw it off into the wind and proceed to fly it at ridiculous speeds, oftentimes only a meter or two from the ground. And you know that every turn is an opportunity to screw up and put it into the ground. So it's a very exciting challenge. So you add that to the engineering challenge of trying to develop these structures and come up with ways to design and build the fastest glider that you can that will still stay together in the air. Another aspect is you never look at hills and mountains the same anymore after you've got into DS. You're always looking for the next hill that has a better separation layer, a cleaner DS zone, and faces the right direction for the wind. So you take this elusive combination of events of being in the right place at the right time with the right glider, the wind direction is right, it's not raining or snowing, and you're in the right frame of mind to take on this piloting challenge. And I was absolutely hooked right from the start. So I had to try my hand at designing my own plane, and this is what I started with many years ago. It's a 1.5 meter span wing. I wanted to start small because I'd never molded an airplane before. I had never designed an airplane before. So first thing you notice is it's a T-tail. And back in the day, in this time frame, T-tails were not really appreciated by most glider guys, most RC glider guys. A lot of full-scale gliders are T-tail, but the RC stuff, everyone felt that the weight necessary to make it strong enough and stiff enough was too much of a bad thing for gliders. Well, it turns out with a dynamic soaring glider that weight is not really your enemy. It actually helps us to reach the lift coefficients for optimum efficiency. This wing was designed with HN airfoil that's designed around this concept of using snap flap. It's a variable camber idea where you camber the trailing edge of the wing, the flaps and the ailerons can come down, increasing the camber of the wing, and we do a programming trick in our radio that allows this to happen automatically as the pilot deflects the elevator. So I'm going to get into that a little bit more on the next slide. You notice the fuselage is fairly small cross-section. Any extra material on the fuselage is basically just along for the ride as drag. It slows you down. There's not much equipment that goes into these things. There's a battery up in the nose, a receiver, and then an elevator servo in the tail. And so there's not much to it. There's no reason to make these big, fat fuselages. So this plane quickly broke the 60-inch record at 250 miles per hour and proved itself as a contender. That was a very rewarding thing to see that I hadn't done something completely stupid with my first effort here. So back to that snap flap idea. Here you've got a drag puller for the airfoil used on the wing. And you can see that we have drag on the x-axis, lift on the vertical axis. And you can see between lift coefficients of 0.1 to 0.3, we enjoy very little drag. It's called the drag bucket. It's where you want to operate the aircraft. But if you get outside that zone, the drag increases pretty rapidly. And so what we can do is we can camber the wing. If you see up here, you can see the shape of the camber increasing. And that has the effect of shifting this drag puller up and down the vertical axis. So now, if we zoom in, not only do we have this peak that we were dealing with before, or this belly of the curve where we'd like to operate, we also have one down here, we have it up here, and up here. And so you can imagine if we correctly program our radio so that the flaps come down at the right progression with elevator travel, we can end up traveling a curve like the red one here, which enjoys nice low drag all the way from 0 to 0.5 lift coefficients. It adds a lot of versatility to the model. And this was one of the things that I think helped make the 60-inch Kinetic successful. And it was one of the first things I learned about aerodynamics. So as things started to progress with dynamic soaring, the speeds increased, and we had to tackle these problems of mid-air failures. The spar bending failure was actually a fairly easy problem to solve. Adding more carbon to the spar was a simple thing. People just weren't doing it. Everyone had this old school concept in their mind that gliders have to be lightweight to work, and that doesn't apply in the dynamic soaring world. The next thing we had to do is fix the flutter problem. And we did a trick where we lock out the flap servos. We added a third bearing to the flap servos. And then we figured out that when we ballast up our gliders for strong winds, if we span load this ballast by putting it outboard on the wing, it has a lot of benefits to it. And then we also had this problem that radar guns were a limiting factor at the time. There's not much of a market, I guess, for radar guns that go over 310 miles per hour. So I made a habit of spending a lot of time on the phone for a long time with radar gun companies, trying to talk them into producing something that would work better for us. And so we'll get to that. So here's a picture of this locked out flap concept. Servo motors, which operate the control surfaces, are embedded in the wing, and they inherently have gear lash. If you were to grab the control surface here and try to flex it with your hands as if the air was going to try to do as it's flying, you would normally notice the servo arm rotates due to the gear lash built into the servo. And this creates an elasticity, sort of, that allows Flutter to come in at a much lower speed than it should. And so we figured out that if you orient the servo arm exactly in line with the pushrod linkage, then you can eliminate gear lash entirely. It's no longer part of the equation. So that was a big step in delaying the Flutter speeds to a speed range where we weren't able to get to yet. And then the next was, after we had eliminated gear lash, we figured out that the only thing left was bearing slop. From inside the servo, we have a bearing here and a bearing here, and then you've got this servo arm conveniently cantilevered out on the other side of both of them, allowing a good bit of flex to happen as the control surface is loaded. By adding a bearing out here on the outside, you remove that entirely. So with this kind of a control setup, it's absolutely rock solid. You can grab the flap, and it feels as if it's glued in place. There's no movement whatsoever. So this span loading ballast concept that I mentioned before, it has a couple of great purposes. As you can see, the lift acts outboard on the wing, and that causes a bending moment on the wing, which was causing these spar failures. Traditionally, people would add ballast to their glider inside the fuselage. It's where there's some room that's accessible, and it's just what everyone did for years. That would have the effect of making it worse. It would increase the bending loads on the wing. But if we instead put this point mass out in the wing tip, it does a couple things for us. It generates this opposing bending moment, which unloads the wing, makes the spar have a lot easier time surviving, and it also has this effect of increasing the roll inertia of the glider. As we're flying in DS, we're in strong winds, it's always turbulent. So the air is always trying to have its way with your glider, rolling it off axis. As one wingtip enters a different direction gust or another air pocket in a different velocity, and the glider's always being rolled around, the pilot's always having to fight it. And moving the control surfaces this actively doesn't do great things for minimum drag configuration of the wing. So when you add this point mass, the plane can fly through this turbulent air and not be quite so upset by the aerodynamic loads. The mass takes over and helps stabilize the plane. So the radar gun companies, I finally talked custom signals into making the Falcon DS radar specifically for us. It even got the initials DS. And then not long after that, Applied Concepts, much larger company, came out with the Stalker Pro, which is good up to 850 miles per hour. So I think we have some breathing room between this problem of radar guns holding us back. So in the world of gliders, bigger is almost always better. It's easier to see when you're flying. It's much more stable as you're flying through this turbulent air. It's easier to keep on course. And when you make a wing larger in chord, the Reynolds numbers increase. Higher Reynolds numbers always equal more efficiency out of their airfoils. The negative of going bigger is we have structural problems. Structural problems increase exponentially when you scale up. And so it gets to be an impossibility at certain scales and just an expensive nuisance at other sizes. So from an X model, I decided the sweet spot was around a 100-inch span or 2.5 meters. And I was lucky enough to work with Dirk Pflug, who's here in the audience. He's a resident of Munich, and he developed a laminar flow airfoil for this model. And the wing was designed a medium aspect ratio, I would say, so that we could still make it very strong, but still gain some efficiency improvements from higher aspect ratio. And a 100-inch or 2.5-meter wing, you can imagine, is a bit difficult to transport. So it has to be made in multiple pieces, generally. And typically, people would split the wing right here at the root and put a joiner in the middle. And that's how most competition gliders are assembled. But that happens to be, for us, right where the bending loads are maximized. It's not a good place to be trying to work out the details, the structural details of a joiner system. So I decided that by making it a three-piece wing and moving the joiners out to about here, we could get the joiners out of this high-load area, as well as use steel joiners to get some of that span loading effect that we were talking about before. And that worked very well on the maiden flight. The 100-inch Kinetic DP set a world record speed of 309 miles per hour at Norco Hill in California. And in the following couple of years, it set the record 11 more times, all the way up to 498 miles per hour. So it seemed to be working very well. The laminar flow airfoil concept is something that helped us reduce the drag on this model. You can see a typical airfoil has the point of maximum thickness very close to the leading edge. That's how they've always been designed. And that has the effect of the boundary layer of air that's up close against to the skin of the wing remains laminar as long as the thickness of the wing is increasing. Once you reach this point of maximum thickness and you have adverse pressure gradients trying to suck that boundary layer off the wing, the boundary layer quickly transitions to turbulent and produces more drag. The goal of a laminar flow airfoil is to move this point of maximum thickness much farther aft. And as a result, you gain a much longer laminar run on the upper surface of the airfoil, thereby reducing drag. The consequence of this type of design is that the surface of the wing has to be pretty close to perfect. Any waviness or deviation from the designed airfoil contour means that you won't achieve this long laminar run, and the reduction in drag simply won't come. So that means we have to move to CNC cut molds, and we have to use quality materials like aluminum to make our molds from. And it's a little bit hard to get what this image is until you study it for a second. It's a mold for the elevator, for the horizontal stabilizer on the K100. And it's been polished to a mirror finish. You're looking at a piece of paper and the reflection in the piece of paper in the mold surface. So you can see that the molds are pretty close to perfect after many hours of sanding and polishing. So after the success of the 100-inch Kinetic, and I got a little bit further down the road with my understanding of what was happening with DS and a better understanding of aerodynamics, I came to realize the distinct advantage of aspect ratio in terms of dictating what the maximum vehicle speed can be for a given wind speed. So in a search for more aspect ratio without having to make an entirely new set of molds, I decided to replace the center panel of the 100-inch Kinetic with a 70-inch. It was 40 inches, now it's 70 inches. We increased the span up to 3.3 meters. And that had the effect of increasing the aspect ratio up to 17.5. And we found that the 130-inch Kinetic was typically 10 to 15% faster than the 100-inch on a given day. This model did set the previous world record speed of 513 miles per hour at Weldon, California, less than a year ago. So it definitely worked, increasing the aspect ratio. So with this newfound knowledge of designing these larger models, and they've been very successful, I wanted to go back and design something smaller that would take some of what I'd learned and apply it to a smaller, more affordable package for people that they could fly in a wider variety of locations. And so I made a 2-meter version of the Kinetic. Again, Dirk Flug was kind enough to work with me on this with a suite of airfoils. And the aspect ratio you can see is almost the same as the 130, but not quite. There's some limitations due to the servo size. You have to cram a lot of things into the wing between the spar and the servos and the control surfaces. It gets to be a bit tight. So to go much higher aspect ratio would require innovation in the servo market. The plane was designed for higher lift coefficients. We're working the wing harder than on previous models. And this is in an attempt to gain a higher lift to drag ratio and more efficiency. The effect it has is it makes it a really fun plane to fly. A pilot that's very aggressive on the sticks and likes to pull a lot of elevator is well rewarded with spectacular performance and a whole lot of fun. We've put a device in our planes to measure what's going on, measure airspeeds, Gs, and that sort of thing. And we've measured over 120 Gs of acceleration. That's our peak, and that's the highest the sensors could go. So we don't know exactly what the maximum was, but we do average on a typical DS session. We're averaging 60 to 80 Gs the entire time. So you think of that, and you put it in perspective. A fighter pilot, I think, pulls maybe 8 Gs or something like that before they start to pass out, and that's with a lot of practice. So it's interesting to note that we're orders of magnitude higher in terms of acceleration. So the 2-meter Kinetic did set a 2-meter record for this wingspan of 462 miles per hour. So it's quite fast for even despite being a smaller model. So these days we're flying in a different realm than what we used to. We're now well into the transonic realm where the compressibility of air is now a factor. At lower speeds, you can treat air as an incompressible fluid, and the models hold up. The computer models hold up. But at this point, we have absurd airspeeds going over the surface of the wing. As the wing travels through the air, the vehicle Mach speed might be only 0.3, but the air is being accelerated by the wing. And you can see that in this case, based on roughly 500 miles per hour, the airflow over the front half of the upper surface of the wing is in the red zone, which is Mach 1.25, or speeds that I can't even really fathom. I think it's 950 miles per hour. I didn't even want to put that because it seems unrealistic. But 1,450 kilometers per hour airspeed over the upper surface of that wing. And what you can see here is what they call a lambda shock wave forming on the upper surface of the wing. It's where the supersonic air has to decelerate. The airspeed on the bottom of the wing and the top of the wing have to match when the wing has passed. And to do that, the air has to decelerate very rapidly. The only way it can do this, due to the elasticity of the air, it can't communicate upstream any longer because we're right at the speed of sound. So it has to do it through a shock wave. And this shock wave has the effect of detrimental effect of ruining the performance of the wing downstream of it. The boundary layer can separate. It's always turbulent, and it's always more drag than you wish. This graph here can show you graphically the effect of that shock wave forming. If you look at lift coefficient of 3, the blue curve here, we have this term, the drag divergence Mach number. It's the Mach number of this, or the speed at which drag rises exponentially with increasing Mach number. And you can see the blue curve here. It happens to be right around, we'll say 0.74, 0.75. The drag starts to go off the charts. At a higher lift coefficient, 0.6 for the red curve, it comes in at an even lower Mach number. And so you can see with gliders where we're trying to pull this, we're trying to work the wing fairly hard the entire time. We're fighting this uphill battle of this drag divergence Mach number getting lower and lower. So it's fighting against us. So the next thing that also factors this drag divergence Mach number is the thickness ratio of the wing. And the thicker the wing, the easier it is to make a structure, a spar that doesn't fail, and to fit servos in it and all that. So we love thick wings. But you can see what it does to this drag divergence Mach number. If you get up to 16% thickness on the wing, you're hitting this drag rise down at Mach 0.68, and that's not going to get you very fast. So if we could make a 6% thick wing, it would be wonderful. We could delay these drag rise problems to higher Mach numbers, and we'd be happy, but we just can't make it survive. So there's a lot of trade-offs in this transonic realm. The next thing we noticed happening with these speeds is a sharp decline in the maximum lift coefficient that the wing can achieve. If you look at the graph in the middle here, that's lift coefficient versus alpha. And really just forget the curve, but look at where the curve ends. For a Mach number of 0.6, we are almost able to achieve a lift coefficient of 1. That's a nice lift coefficient. You can do a lot with that. But as the speeds increase up to Mach 0.8, you find that we're down below a 0.4 lift coefficient. Well, that's our design point. We can't really deal with that, right? That led to some issues, and you can see what happens.
446. Oh no.
Pardon me. There was another one in the same general time frame, maybe a couple months off from these. I can only work so fast building them again. But there's another one that even crashed, similar failure mode. And I got I got very frustrated and had to figure out what was going on. What we figured out after I sat down with the graph that we just looked at that showed the decreasing lift coefficient, and realized that this crash was typically happening just after a very strong roll correction had to be applied due to the turbulence on the backside of the hill. And as you apply a strong aileron correction, the downward traveling aileron has the effect of increasing the angle of attack of that portion of the wing. Also increases the lift coefficient of that portion of the wing. And what I figured out was happening is we were increasing that lift coefficient beyond the maximum that the wing can generate under this transonic condition as it's been decreasing with speed. And we're having a localized tip stall, and the plane would roll violently and go upside down and crash into the hill. So we did figure out some solutions to this. If you recall the snap flap conversation we were having earlier about the camber on the wing being linked to the elevator, we were able to reprogram the snap flap so it only acts on the inboard control surfaces. And this has the effect, when the elevator is pulled, has the effect of aerodynamically twisting the wing so that the root of the wing is flying at a higher angle of attack and higher lift coefficient than the tip. This leaves a little bit more margin for the aileron to do its thing without exceeding the stall lift coefficient or stall angle of that portion of the wing. When you have a stall at the root of the wing, it's not such a bad situation. The plane maintains its roll attitude, roll configuration, and you can recover. It just doesn't turn quite as tightly. When you have a stall on the outboard portion of the wing, that's when you get that violent rollover and things go poorly. So I did experiment with a swept wing design to try to mitigate these issues before we figured out this reprogramming of the radio. And by sweeping the wings aft on a plane like this that's going in the transonic realm, you're able to delay these transonic issues. If you imagine the airfoil, the flow-wise airfoil of the wing, what the wing sees is affected by this sweep. The Mach number that each portion of the wing sees is reduced by the cosine angle of the sweep. And so if the vehicle Mach might be a 0.75, but if you've swept the wings, then you've got a cosine angle reduction of that effective Mach that the wing feels. So you can delay these problems a little further. We did find that it flew okay. We didn't fly it in massive winds, but it flew not so great at lower speeds and had some behavior that any swept wing is less desirable than a non-swept wing. They're just not as well behaved and as efficient. So I decided to shelf that idea and instead concentrate on what's the best we can do without resorting to wing sweep to get it done. And that led to this latest development, the Transonic DP. The aspect ratio, as I mentioned before, was the key to higher efficiency, but it's structurally limited. If you can imagine trying to make a really long, skinny wing to get this high aspect ratio, it's just not going to hold up. So there were a couple things we were able to do to help mitigate these problems. The wing is made from one piece. It's not easy to transport, but I have a pickup truck and a camper shell. I can pass it through the window, and anytime you make a wing into multiple pieces, you reduce the structural integrity of the wing. So this one-piece wing design helps matters. If you notice, the wing is shaped with very skinny tips and a healthy root chord, but a very skinny tip chord. This taper ratio helps to reduce the aerodynamic loads on the wing. There's not much wing area out at the tips, so the center of lift is closer to the middle line of the glider, generating smaller bending moments. Also, the torsional loads on the wing are reduced in the same manner. Again, Dirk Flug was kind enough to work extensively on the suite of airfoils for this wing, which were designed with transonic speeds in mind. And he was able to work together with Stuttgart University using a program created by Mark Drella at MIT called MSES, which handles accurately the modeling of the wing in compressible transonic realm. So the model was designed to reach 575 miles per hour before we hit this horrible drag rise. And on April 13th, it set a new world record speed of 519 miles per hour, 835 kilometers per hour. And I have a video clip here of that. Okay. Hear the turbulence on the microphone, and you'll see some deviations.
494.
There we get some turbulence.
I'm glad I know the guy who built this thing. Structurally speaking.
So my radar gunner was having a problem with the gun. It was in a mode where it wouldn't remember the peak speeds.
Almost looks like tip flutter.
So he was just having to keep an eye on the gun to see the speeds as they popped out.
It's
I
not
saw
the
5 something. I saw 505, 519.
519.
So that was quite the windy day. Thank you. I thought it interesting to look at the history of dynamic soaring speed records since the year 2000. That's when they really started keeping track of who had gone how fast. And you can see there's steep progress at some times and pretty slim progress at others. This near vertical climb here represents the new radar guns hitting the market. And then we've had a very steep climb here for the last number of years, until we've reached this bit of a plateau that's hitting the transonic wall with the current designs, that drag rise that we were looking at on the graphs earlier. There's also a factor here that doesn't really, unless you're a pilot, you don't really see it in the graph, but pilots have to develop the skill set to fly these speeds. Every time you go out and you fly faster than you have before, you get this feeling like you're in over your head and your brain can't stay ahead of what's happening. It's a very difficult thing to keep up with. It's the human factor of dynamic soaring. And if you picture this, the constant lift coefficient means a constant diameter circle. If you maintain that constant diameter circle, as speeds increase, the time to complete the circle decreases. So the faster we go, the faster we have to think. And the minimum orbit time that myself or a skilled DS pilot can maintain is roughly 2 seconds. Anything less than that, and it becomes very sloppy flying and very inefficient. And scientists have studied the response time of humans, average humans, and what they call the choice response time is if you have to respond to a stimulus and not only just respond to it, but make a choice. So the turbulence rolls your glider, and you have to choose which way to move the stick to correct from that, to maintain your heading. And that's about almost half of a second. And at 519 miles per hour, the plane has already traveled 100 meters before you've it's even seen an input from the pilot. And at times we're only 5 meters from the ground. So you can see that there's not much margin for error at these speeds. So what's next? I'd like to push the Transonic past 575, its design goal. And once we get to that point, Dirk and I will be working feverishly on a new swept wing design to take us into further speeds. And I'd like to pursue this practical application of what we've learned over the number of years we've been DSing to put it to practical use and figure out what else can we do with this concept. Albatross, go back to the original inventor of DS. You can imagine a UAV which takes advantage of this flight pattern to traverse open expanses of ocean with no outside energy needed as long as the wind blows. Well, if the wind doesn't blow, we could add solar panels to the top of the wing. The plane lands in the water and recharges its batteries, and when the wind picks back up, you use the propeller to take off again and begin your dynamic soaring circuit. Could go on for indefinitely. And then another concept is this idea of de-icing the jet stream. The jet stream has a vertical velocity gradient where you might have 100 mile per hour winds at 30,000 feet. And I apologize for the units. But down at the ground level, the wind velocity is 0 right at the ground. And this velocity gradient, although it's not as abrupt as what we use on a ridge for RC gliders, it is enough. It's not enough to go fast with, but it's enough to sustain flight. You could conceivably drop a plane like what you see on the right here out of an airplane at 30,000 feet, and it'll come right back. And it'll keep on doing it as long as the jet stream remains active. Lehigh University has been working on that concept. It's called the jet streamer, if you want to look into that further. So now's when I'd like to ask you guys. We have a room full of really smart guys, and I've been racking my brain on this for a number of years, and now I need some outside ideas. Where can we go next? I've heard it's really windy on Mars. And looking at the surface of the planet, I notice it's filled with these craters. And what's a crater but the ideal DS ridge wrapped 360 degrees around? Any direction, any wind direction, you got your DS ready to go. So that's it. If I'd like to open it up for questions. If anybody has anything that's weighing on there, sure.
How do you land safely?
Well, we have flaps on the wing, so we can drop the flaps, and we drop the speed of the glider down to a reasonable speed, roughly, I'll say roughly 30, 40 miles per hour. And then we land on the top of the slope, hopefully not on rocks. And you retract the flaps quickly before you touch the ground. Yes?
How many birds were killed?
I am aware of one case in Switzerland of a guy. In fact, it's the European speed record of 380-something miles per hour, I believe. And yes, he did have a bird strike, and both birds were killed. Yes?
Did you ever test electronic stabilizers?
Yes, there's a friend of mine, Alan Cacconi, in the U.S. has been very active in this area of dynamic soaring, and it works magnificently. The plane almost all but flies itself. You put it in the correct trajectory, and you pull the elevator so it makes the right diameter circle, and you don't really have to do much at all on the roll axis.
Why are you not using it?
I guess I'm an old school guy, a bit of a purist. I actually savor the human aspect of dynamic soaring. When we get to the point where I can send my plane up to the hill, I don't even have to go any longer. I just send it with my friends and tell them, and I look online and see what my best speed was. Where's the fun in it? You know, it's a different kind of thing. I value the research aspects of it, and I value the instrumentation for collecting data and these things. But from an entertainment standpoint, a recreational activity, it has nothing for me. I love the adrenaline and the excitement of feeling the air. You can actually, you learn by what the plane does, you feel what it's encountering. And then it's like playing a video game, except when you crash, you can't press the reset button. It's really addictive, though, and I value that aspect of it.
A question regarding the videos and the laser speed measurement device. Yeah. I forgot the name. How do you track the plane? Because it's going quite fast.
Yes, we actually use radar. We've tried a number of different things. LiDAR hasn't been, it's hard to aim LiDAR. Radar has a broader cone. By the time it reaches the plane, it's easier to hit the plane with the radar. But we do have problems in that all of the airplanes being optimized for aerodynamic low cross sections, they're also low radar signature. They're also made of carbon fiber, which tends to be a stealth material. But radar, we decided on that as the universal standard worldwide because airspeed has issues that you measure this indicated airspeed. It has to be corrected for temperature, and it's hard for pilots to know the temperature, exact temperature, and actually make the corrections. And radar was the one standard thing. It doesn't depend on the wind speed. It's anchored to the ground. It's easy for everyone across the world to compare their speeds with each other, apples to apples, fair comparison.
Did speed windsurfing, and there the measurement problem is also existing, and what people did was using differential GPS,
Okay.
which is quite successful.
Would be, except that consumer GPS loses its lock on satellites around 4Gs. We've been down that road before, and if anybody knows how to get their hands on military-grade GPS, we should have a talk. And also, before I let everybody go, I do have business cards on the table. If you are interested in dynamic soaring, I want to make sure that you know to come and grab something so you can contact me later.
I wonder why you ever see Mach-buffeting effect.
We haven't been able to identify it specifically. On days like that, when the speeds are high, it's pretty crazy out there, and it's hard without really good video to identify exactly what is happening. That's why it took so long to diagnose this tip stall problem. it's possible. It's likely. If we haven't had it yet, it's coming. So yeah, good point.
What's the, why do you use T-shaped tails?
The T-tail has a couple of great effects. One is since we're always making a turn with dynamic soaring, the wing is always, the ladder is always pitched up, which drops the tail. A cruciform tail or a V-tail would be obstructed by the wing wake off of the wing, the turbulent air coming off of the wing. It would be less effective. By putting it up on the top of the vertical stabilizer, it gets it nice and clean in the clean air, and it's most efficient. Also has the benefit of keeping it out of harm's way when landing in bushes and that kind of thing.
Okay, I'm afraid we have to stop here now to give the next talk a chance to stay in his time slot, but I think Spencer is definitely here for the rest of the day, and
Sure.
I would like to thank him for his speech first.